Welcome to my channel. The goal of this project is to implement a simple PID controller using a FPGA. Let's see how we can control a ramp's angle so that a card is always returned to the center. When the card is pushed away from the center, there are three factors that affect how it is returned. First, there is proportional gain. We can easily see that the ramp angle increases as the card moves away from the center. Next, let's think about what will happen if the card is close to the center, but not quite there. Since the card is close to the center, the proportional gain would be small and our card would be stuck. Integral gain is used to raise the ramp angle over time so that our cart can reach the targeted location. Finally, how do we make sure that the cart doesn't go past the center on its way down? If our cart is quickly approaching the center, we will make an extra reduction to our ramp angle so that the cart doesn't overshoot the target. This is called derivative gain. Let's look at some of the hardware that is used in this project. In the previous video, we saw that there was an ultrasonic sensor on the left side of the ramp. This sensor allows us to measure the distance to the cart. In order to obtain a reading from the sensor, we must send a 10 microsecond trigger pulse. We use a voltage translator to convert the 3.3 volt logic from the FPGA to 5 volt logic required by the sensor. After the sensor outputs a signal, we use another voltage translator to convert the signal back to 3.3 volt logic for the FPGA. Now, let's see how we can physically control the stepper motor using the FPGA. This project makes use of a stepper motor driver board. Whenever the FPGA provides a pulse to pin 7, the stepper motor increments by 1/8 of a step. The stepper motor direction is controlled by pin 8. So how do we actually use our FPGA to process the sensor data and turn it into motor control signals? The FPGA design is broken into 3 distinct modules. The first module handles all the interactions with the distance sensor. If we take a look at the timing diagram for the ultrasonic sensor, we can understand how we will want to set up our logic inside the FPGA. The first requirement is that we send a 10 microsecond trigger pulse. After this, the sensor handles transmitting and receiving a sonic burst. Finally, the sensor module outputs a signal that has a pulse width that is proportional to the distance of the object. In order to send the trigger pulse and compute the cart's distance from the sensor, we make use of a state machine. Let's take a look at some code. During the idle state, we reset various counters and wait until we receive a trig enable signal. The trig enable signal comes from a switch on the FPGA. We then transition to the trig state where we send the 10 microsecond pulse. Since our FPGA is clocked at 125 MHz, we will need to wait for 1500 clock cycles for our pulse to complete. Next, we wait for an echo to be received by the ultrasonic sensor. If no echo is received within 60 milliseconds, we will send another trigger pulse. When an echo is received, we will convert its duration to a number indicating the cart's distance from the sensor. At 125 MHz, 125 clock cycles is equivalent to 1 microsecond. By counting the number of microseconds the echo is received for, we can multiply by a conversion factor and obtain the cart's distance. This distance is passed on to another module in the FPGA. Finally, we wait for 60 milliseconds before sending another sonic burst. This is done to prevent interference between the trigger and echo signals. Let's take a look at our next module. Since we have the distance, we can now perform our PID computation. We make use of another state machine. Starting with the idle state, we wait until we receive a distance indicating where the cart currently is. Once we have this distance, we can compute the error between where the cart currently is and where we want it to be. We also save the previously computed error. In the next state, we have some supplemental logic that adds an error dead zone and handles some overflow issues relating to the integral gain component. Finally, we reach the state where we compute our individual PID gains. Notice the differences in how the gains are computed. SP is proportional to the current error, SI is proportional to the sum of error over time, and SD is proportional to the difference between the current error and previous error. We can now add our PID gains together and perform a scaling operation so that the new ramp angle can be achieved by the stepper motor. We also include some saturation logic so that the stepper motor doesn't go beyond 90 degrees in either direction. I'll include a link to the project repository in the video description. Before moving on to the final module, let's see the simulation for the PID computation. The simulation shows the cart starting on the left side of the ramp and moving to its center. Error is shown in red, the PID components are shown in orange, and the computed ramp angle is shown in yellow. By properly adjusting the scaling factor for each PID component, we can have our cart reach the center more quickly. In the final module, we translate our computed ramp angle into physical movement of the stepper motor. A position counter is set to 0 during the setup state. We then monitor whether the computed ramp angle is greater than or less than the current ramp angle. We will then either raise or lower the ramp until it has reached the computed ramp angle. In order to actually make the stepper motor move, we use a separate state machine to send our pulses and desired ramp direction to the motor driver board.